Hi guys, welcome to this last 3 units, basically dealing with the topic of cosmology, basically the universe as a whole. I know we covered a lot of materials up to this point, so now we're taking the entire universe as a single subject. Remember that Mr. Hubble, let me share with you this something in here. Let me find the OneNotes so that I can write on. I know, guys, you're supposed to do the reading. Please do the reading and make sure you go through all of these things. All the units. I know I posted a lot of stuff for you guys, summary and also PowerPoints. You're supposed to have the book to go through it. So I'm just going to cover the main ideas in here, hoping that you guys complete it. Don't forget that you have an exam, midterm coming next week. So you really have to make sure that you go through the review and prepare for all of the topics and do all of the assignments as we are toward the end of the semester. So again, right around the beginning of the century, before that, there was actually a debate whether or not the entire universe is our own galaxy, which is the Milky Way, or does it expand beyond the Milky Way galaxy? Excuse me. And there was a debate that was actually in the around 1920 about the issue of whether how can we go about determining it, and the debate was not settled between the astronomers at that time until Mr. Hubble was looking at this type of Cepheids, which is a kind of stars that have a specific kind of brightness, basically, that changes, that fluctuates with a given frequency, and that frequency is really dependent on their luminosity. So basically, if I can find the frequency, I know how luminous that star is, or that actually Cepheid is, which is a combination of actually variable stars. So in this case, this variable star, if I know the frequency, all I have to do is basically look and see how the light changes, dims and changes, basically dims and brights, dims and brights. So I know how long it takes to do it per second, and that's what the frequency is. Then I can find the luminance of that star, how much energy is basically emitted, energy, that's what the luminance is, per unit time from that star, okay, per unit area. Now, if I know that, then I compare that to the brightness of the star. If it is bright, that means it's nearby. If it's dim, that means far. So basically, if I can find the luminance based on the frequency, I can measure the brightness, then I use the fact that the brightness is simply equal to the luminosity divided by the area where the light spreads, which is in this case 4 pi times the area, which is in this case the distance squared. So if the star was here and it's going to emit in the entire space, which means its luminosity will expand through a sphere, the area of the sphere is 4 pi times the distance from where I am looking at it. So if I'm here looking at it, it's going to spread through the entire area. If this is far away, it's going to spread through a bigger sphere than if it's nearby. Basically, the Cepheids allowed Mr. Hubble to determine the fact that the Milky Way is not the entire universe, and the universe is made up of other galaxies. He focused his initial observations on Andromeda, and it turns out that Andromeda is well outside of the Milky Way, because the estimates at that time for the size of the Milky Way was around 100,000 light years across, and he came up with an estimate around 1 million light years. The correct answer, of course, it was corrected later on to be actually twice that much, 2.5 million years. So it's even further than what he estimated. But it's still, even with his estimate, he found that the Andromeda is well outside of the Milky Way. And then furthermore, there are all kinds of fuzzy objects in the sky that were classified by Mr. Messier that turned out to be actually galaxies further than even Andromeda. So the universe was big. Then the other thing that he started noting also for those faraway galaxies, he saw that the light, at least the spectral lines for hydrogen, for example, was shifting toward the red. So the spectral lines were red-shifted. And this red shift indicated that they are moving away from us. So he tried to determine the velocity with which they move away. He found this relationship, that the velocity is proportional to how far they are. So I'm going to label this as R. I know the book put D, but it's still, I mean, you can put D or R, it doesn't matter. So if you're looking at them in here, in this, this is our location in the Milky Way, and we're looking at the faraway galaxies. We're not looking at Andromeda or Triangulum or any of the nearby galaxies. We're looking far, far away galaxies. Those galaxies, they seem to be moving away from us in all directions. So that's why I use R in this case, because when you look at the sphere, when you are in the center of the sphere, that is the radius. So anywhere you look, all the galaxies are moving away from us, and they are moving at this velocity, meaning the further or the farther the galaxy, the faster it moves away. That's basically what the whole thing is. So basically, the universe is expanding. The universe is expanding. Before that, Mr. Einstein proposed a theory called the general theory of relativity. And in his theory, everything can be understood beautifully, including the oddities that existed in Newton's work. But his work actually explained a lot of things. But there was a problem with Mr. Einstein's general theory of relativity in that the universe was not stable. When he solved his equations, Mr. Einstein found that the universe collapses immediately on itself. So Mr. Einstein introduces something called the cosmological constant. That constant was put manually in his equations, so it did not really derive automatically from his equations. So he added a constant just to prevent the universe from collapse. But then when Mr. Hubble discovered that the universe was expanding, then there was no need for that cosmological constant. And he said, wait a minute, then we don't need it because the universe is expanding. Ultimately, probably is going to collapse on itself. But the point being in here, the universe is expanding. So the solution then is fine this way. So it must have started from somewhere. And that starting point in here, which was the origin of the universe, is what is known as the Big Bang. Okay, so this is where the idea that started. So the universe is expanding, and that's what Mr. Hubble has discovered. This constant H is what is known today as Hubble's constant. So this is Hubble's constant. As a matter of fact, Mr. Hubble himself invited Einstein to the observatory, the Griffith Observatory here in Los Angeles, and basically showed him that, hey, this is basically what we looked at and all of that. So Mr. Einstein, that's why he scratched his constant, the one he added manually to his equations. And he called this the biggest blunder in his life. So basically, that's the point that at this point, that's where the story ends, at least at that point. But remember this story because it's going to come back again. The point being in here is that this is what Mr. Hubble has discovered. Now, this redshift has a value also that you can mirror. Remember what a redshift is. The spectrum, if you look at the spectrum, for example, of hydrogen, at least in the visible range, there are those four famous lines that we saw them, at least for some of you guys who are sitting in the lab, we saw them in the lab. So the point being in here, this is their natural position. This is where the red is, and this is where the blue is. Okay? Now, and there is the spectrum in between them, so all kinds of colors in here. So the point being in here is that they're not in that location for other galaxies. You'll find them in here. So this line will be moved in here, this line will be moved in here, this line will be moved in here, and this line will be moved in here. So basically, they are all shifted toward the red. That doesn't mean that they are red. It means that they are closer to the red than what they normally should be, okay? The difference in wavelength in here, so this is where the wavelength is supposed to be in the laboratory. This is where this wavelength was found. The same thing, this wavelength is supposed to be here, but this is where it was found. The change in wavelength, delta lambda, namely the longer wavelength, because remember, red is longer than blue. So the new one is lambda minus lambda naught. Okay, so lambda is bigger than lambda naught. So this is, they get longer. They are stretching. So the wavelength and the waves are stretching to a point that the wave is not like it used to be here, but rather it's like this. So from this point to this point, it's stretched and this is the stretch. This is the difference between them. This is what I mean by delta lambda. If you take this value and you divide it by lambda, this is what is known also another definition of the redshift, the Z value for the redshift, okay? So this is the Z redshift. This is basically a value that determines how far is this redshift. It's a relative redshift in this case. It's not measured exactly in nanometers or units of the wavelength, because you take nanometer, you divide it by nanometer, it cancels. This value in here was observed, at least according to the book, up to the value of 12. Now we know actually in the advent of the James Webb that this value is actually, we were able to find even higher values than G equal to, at least the old days was 11 point something or 10 point something. Now we're passing 12, indicating that we're looking at the far reaches of the universe. We are looking almost to just a few 100 million years after the Big Bang. So that is basically how the idea of the expansion of the universe. So that means those stars those galaxies are moving super fast to the point that they are not actually right now reachable. They have already sent their light and went way beyond the observable universe. So they are outside of the scope of basically what we can do. Anyway, the point being in, this is the expansion of the universe, and it's expanding at a constant rate h. So meaning, the further the galaxy, the faster it moves. There is some discrepancy, and I know the book goes about it, about the value of h. It was measured with two different techniques, and there is a difference between the two values. This is one of the unsettling issues that is still trying to fix it. How come h is a little bit different? Why h matters? Because it actually is very, very important value. Let's, for example, say the Big Bang happened in here. By the way, it happened everywhere in the universe. And the universe expanded by value from that from point. It doesn't matter which point, because all points are equivalent in the universe. That is a cosmological principle, by the way, that all of the directions are very similar. So in this case, let's take a galaxy, the Milky Way, for example, okay? The Milky Way has a given mass. Let's give it a mass m, which is a big value in terms of how many solar masses it is. But the point being here is that that mass now has receded from its original location, just like everything else. Because if we are sitting on a different galaxy, far away from our own galaxy, we will be looking at our own galaxy also moving away. That's really the analogy in the book is given by the rising dough, or when you put something in the oven, everything expands in all directions. So the fact that we're sitting in here and looking at those galaxies receding from us, following this law, that the velocity of recession in this case is equal to a constant times the distance of how far they are from us. From somebody else in another galaxy, he would deduce the same thing, that we are moving away from, which means that it's not really we are moving at all. Galaxies are not moving. What is moving is the space between them is being stretched. So you have to understand that, because everywhere you look, they're moving away. So it's not this galaxy or that galaxy that has moved to a point that now this galaxy appears here and this galaxy appears there. No, it's actually the space between them that's stretched, which means also that's why the wavelength also stretched. That's why the wavelength were redshifted. They are actually, the wavelength initially probably was in the ultraviolet region, but now it's stretched so much. Now it's actually in the infrared region. That's how the James Webb actually operates. It works in those frequencies that has been stretched so much that they are actually moved in the microwave and the infrared region. So the point being in here is, this is basically, the idea is, it's not the galaxies are moving, not galaxies are moving, but rather it's the space between them that is stretching. Space itself is stretching, is expanding. That's a very important point to remember in here, because the whole analysis in here is based on that. So if we are in the Milky Way, for example, when it was before it moved away from where it was before, because before the space basically made it move away from everything else, and everything else is moved away. And so it must have traveled the whole distance, which is that r from a central location that I was talking about, okay? Now, it took it a time t from the beginning of the universe. So this is the age of the universe to travel that distance. So it was here when the universe was created. Then it stretched, the entire space stretched to a point now that it is as far as a distance from some reference point. It doesn't matter what that point is. Any galaxy, pick it. Or from our vantage point, a galaxy that was close by now has moved very far away from us to a distance, let's call it R. And provided that it did it in the age of the universe. So what we're trying to find is the age of the universe. Obviously, we can find the velocity in here as just distance over time. That's it. That's what the velocity is. The speed is distance over time. But we know that is also equal to h times distance. This is from Hubble's law. This is what Mr. Hubble has determined based on observation. Okay. So in this case, this expression, if I cancel the r on both sides and move t on this side and move h to the other side, I will find that the age of the universe is 1/h. That's why Hubble's constant is extremely important, because determining it will help us know exactly how old the universe is. So based on meticulous observations, okay, the agreed value on for h is so that this age of the universe is almost 14 billion years. Almost 14 times 10 to the power 9 years. That's it. So we're asking if you find the value of z greater than greater than 12, for example, 13 or 17 that Hubble is reporting, that put them at a distance more than that put them at the distance of about 32 billion years. How could that be? The universe is only 14 billion years, and these things are about that much. Well, those they fell beyond or 14 billion years where the universe is actually right now. So the universe is expanding so fast. At some point, for the faraway galaxies, it's expanding faster than the speed of light. And there is no problem with that, because we're not talking about mass moving faster than the speed of light. This is space itself, which is nothing really. That's what the space itself. So it's stretching to the point now that it is faster than the speed of light for those faraway galaxies. All you have to do is put distances that are incredibly higher in here, and you can find the speed v, and there is absolutely no reason for it to be constrained by relativity or anything else. So this is how we determine the age of the universe based on the observations of Mr. Hubble. There was an unsettling question. If the universe is expanding, okay, because space itself is stretching, okay, is there enough mass to slow it down? Remember, the force of gravity is an attractive gravity. So all of these galaxies that are moving away from each other, all in these directions, they have mass. In mass between mass, they attract. According at least to Mr. Newton's law, the force of attraction is proportional to the masses actually of this galaxy times the mass of the other galaxy divided by the distance between them. Granted, these distances are increasing, but overall, at some point, this effect of gravity will slow down because they're moving against gravity, but that if there is nothing to hold the universe from basically further expansion, the belief was that the expansion ultimately will slow down. So that is really the question. Okay. Here is the answer to that. Let me first of all try to find the critical density of the universe to reverse the expansion. We want to know how much mass in the universe is needed to basically slow it down and then bring it back. If we don't have that density, if we don't have that mass, then the universe probably will stretch forever and ever and ever and ever and stopping. Okay. If we have very little density, actually, everything will fly away like an explosion, basically. So that is the whole point in here. So for that, let's revert. I know we're using classical mechanics. These things are actually better treated with the general theory of relativity, but that's near big masses. But far away, we're fine. We can do classical mechanics. So we're going to say that a given galaxy, it doesn't matter which, given one, let's say it has a mass m. It's a big number. It's usually in the billions of solar masses. Okay, it doesn't matter. You will see that it doesn't matter how much mass you're going to give that galaxy, small or big. Okay. If the rest of the universe is pulling on it, and if this galaxy is moving, as I said, that they're basically they have motion, at least apparent motion. So it has a kinetic energy, this galaxy, and the kinetic energy is 1/2 times mass times velocity. So this is the kinetic energy of the galaxy that is trying to escape the rest of the galaxies, escaping the rest of the universe. Remember, the rest of the universe, I'm going to give them a big mass m. Okay, there are too many of them, and this little galaxy is not going to matter at all. Even if it's a big galaxy, it's not going to matter because you have billions and billions of other galaxies. So they're going to have to dominate it. So ultimately, they're going to probably put it back. So that's the idea. So what I'm going to do is the following. I'm going to require that this interaction, remember the potential energy due to gravity only, that's the only thing that matters at this point, is equal to G times the mass of this escaping galaxy. This is its potential energy with respect to the rest of, this is its mass with respect to the remaining all of the masses, okay? Times the mass of all of the other galaxies combined, which is the mass of the universe really, divided by how far is this one from the center of the universe, okay? So ultimately it was at the distance r, and now it moved to, at a distance in the beginning, and now it moved the distance r from the rest of them, trying to escape everything. Well, it will escape if it has enough kinetic energy. But if that kinetic energy needs to exceed this value of the potential energy, because the potential energy is trying to hold it to the rest of the universe, but if it has enough velocity, it's going to escape. That's basically the whole idea. So at a critical, at least, if you wish, at least it needs a kinetic energy that is equal to the energy that is holding it to the rest of the universe. If it does that, it's going to barely escape. Okay? At least equal to that. If it has more, that's fine. It's going to escape. If it has less, it should not escape. The rest of the universe will bring it back. Okay? That is why I was telling you the mass of the galaxy doesn't matter, because it's going to cancel out from this equation. So any galaxy, small or big, all it needs is this velocity. And the velocity it needs to escape the rest of them is g. Let me move to the 2 to the other side, times 2 times the mass of the universe divided by r. Okay. Let me do a little bit of math in here. Remember, the velocity that Mr. Hubble has found is proportional to that distance of how far it is from where it started from, for how fast it's moving, depending on how far it is. And if we are here and looking at it at distance r, this is the formula that we're going to use. So if this is just at the boundary trying to escape, this is what we use for it. So we're going to plug in back. So we're going to square this number. So it's going to give me h squared times r squared must be at least equal to 2g times m divided by r. If I divide by r squared and do a little bit of manipulations, So I'm going to divide by r squared. So if I divide by r squared everywhere, obviously this r squared cancels that r squared, and this r becomes r cubed. So it's going to be 2g times m divided by r cubed. Here is where the critical density of the universe is. So the universe really needs a critical density that is equal to, the symbol for, even the book uses it for the density is the Greek letter rho. So this is the Greek letter rho, okay? Must be equal to, but the index seen here is at critical. So this is something that we need to watch for. If we find it, that means the universe is going to, those galaxies, they will continue to expand forever and ever. If the density is less than this critical value, that means we don't have enough gravity. I'm sorry, that we have too much gravity and going to collapse the whole universe on itself. If the density of the universe is, did I say less? I'm sorry, I forgot what I said. If the density of the universe is less than this critical value, that means we don't have enough gravity to hold the universe together. So it's going to expand forever and ever and ever and ever. If the universe is denser than this critical value, that means we have a lot of mass in the universe that is going to ultimately collapse it back on itself. So that's really the whole idea. So the density is, we know, it's mass over volume. It's been like this everywhere. And the volume for a sphere of radius r is just, so this is the critical density, is just mass over 4 pi over 3 times r cubed. That's basically a known formula from geometry. Okay, that's the volume of a sphere. Okay, so all I have to do now is plug in, because I need actually m over r cubed, because I ended up with an m over r cubed in here. So I need to pull m over r cubed in here. So all I have to do is multiply by 3, multiply by 4 pi, and divide by 3. This will cancel in the denominator. So it's going to be 4 pi over 3 times the critical density must be m over r cubed. Now I have m over r cubed in here, and I have m over I cubed in here. All I have to do is just substitute this value of the mass of the universe divided by r cubed by this value in terms of the critical density, because that's what I'm trying to find, the critical density. And actually the book gives you that value too. So let me find it, okay? So we ended up with an h squared from the previous one equals to 2g times m over r cubed, the mass of the universe divided by how big it is, divided by the radius of the universe times to the power 3. But the mass over the radius of cubed is nothing but 4 pi over 3 times the critical density. So from here, we can pull the critical density. 2 times 4 is 8. So I will have 8 pi times d divided by 3 times the critical density. All I have to do is multiply both sides of the equation by 3 over 8 pi g, and this term will cancel from here, and it's going to reappear in that side. So that means the critical density must be equal to 3h squared divided by 8 pi g. You see why determining h is critical? Because g is just a constant. G is just that Newton's constant, which 6.67 times 10 to the negative 11 Newton meter squared divided by kilogram squared. Okay, so it's just a constant. But h, Hubble's constant, which has the units of a 1 over second, by the way, it has the units of a 1 over time. Remember, the age of the universe is 1 over h. Then that determines the critical density of the universe. So ever since that observation was made and everything was done, everybody was trying to determine the critical density of the universe. So you go about it in different ways by measuring, for example, the value of h. And as I was saying, h has a little bit of an issue in the beginning. Until now, actually, it's still an ongoing issue because there is a discrepancy. It's either greater than that value or this value, or is it there is another technique, actually sample different regions of the sky, of the interstellar space, basically, and find how many particles of mass in there per unit meter. That's what density is. It's how much kilogram is it per meter is. So if you can find that, and if you know that number, then here is the idea. I'm going to put it symbolically again, and I think that the book also goes about it in detail too. So let's say, for example, the density of the universe is greater than the critical density, or the density of the universe is exactly equal to the critical density, or the density of the universe turned out to be less than the critical density. There are no other fourth option. Either the density is more than the critical, or equal to the critical, or less than the critical. Let's think about it. If the density of the universe is more than the critical value, that means there is too much gravity to reverse the expansion. Too much gravity to reverse the expansion. And so what's going to happen? Then it's going to expand, but then ultimately it's going to run out of energy. So it's going to start to collapse and heat up again until at some point it's going to become a singularity, in which case probably again it's going to expand, go through another expansion. So the universe is some sort of an oscillatory behavior. That is one way. If it is going to be less than the critical value, then in this case I don't have enough gravity to hold it together. It's like an explosion. So the universe is going to expand forever, indefinitely, and controllably. It's like an explosion. And in here, it's going to be marginally, it's going to marginally expand also forever. But this seems to be kind of a, is it really that? To be that value, that specific value? And that's exactly what the observation were at that point. It seems like the universe has this critical density that we just measured. Remember the story of Mr. Einstein with, with Hubble about that blunder that he thought it's a blunder? It turns out to be not really a blunder at all. It turns out to be actually something needed. Because in the late 1990s, there were observations trying to determine this exact same thing that we were talking about, this Hubble constant, and trying to answer the question, how much the universe is slowing down? That's really the question that people had in mind, because there is no question about it going to slow down because of the fact that gravity is there to slow it down no matter what. Even if it has this much density, even if its density is less than the critical density, it's still going to expand forever, but the expansion is going to slow down ultimately, but not reverse. It's going to continue its expansion. So it's like, for example, a car, you have the brakes on and it's going downhill. Ultimately, it's going to continue moving. Probably it's a bad example in this case. Let's say, for example, downhill, that is actually an icy downhill, okay? So if you put the brakes on, it's going to slow down, but not as much as if you don't put the brakes on. And that's exactly what this thing is. So gravity is acting as brakes. It's a braking system. So we know the universe is going to expand no matter what at this point. It's expanding. If it has too much density, so it's going to slow down a lot. If it doesn't have enough density, it's going to slow down, but not to the point that it's a lot. So that's the question that was asked in the 1990s. That's what everybody believed anyway, because there is no other thing that we know other than this. So what these observations were, they were looking at the type 2 supernovae, for faraway galaxies. And those, they know exactly how much also their luminance is, similar to the Cepheids, because type 2 is, they come from basically a neutron star feeding on its companion up to a point when its mass reaches exactly 1.4 the mass of the sun. Then it goes supernova. So we know exactly how much mass it has. So we know exactly how much energy it's going to start with. So we know exactly how much our energy output is going to have. So we know exactly how much luminosity is. Now, if we know how luminous these things are, and if we can measure their brightness, Then again, we go back to the same formula that I mentioned in the beginning for the Cepheids. It's the same technique, trying to find how far that thing is, namely this one. If you know how luminous those type 2 supernovae, not the Cepheids, all you have to do is, and then if you can measure how bright they are, then you can determine how far they are. Okay, and go back and measure this redshift, and now you can find the value of h, and you're going to be happy. You're going to know how much the universe is actually slowing down, to the surprise of everybody. They didn't find the universe is slowing down. That was a major shocker for everybody. The entire scientific community was shook to the roots, because where is this thing coming from then? It seems like not only the universe is not slowing down, it's actually accelerating in its expansion. Which is a mystery. Something is acting as a negative pressure. Something is acting as anti-gravity, pushing the universe away from where it is right now. Actively doing it. Actively doing it. Not, it did it in the Big Bang and then now that's it, that agent is stopped. It's actually pushing the universe to beyond that. So this whole thing then, first of all, that answers this question altogether. The universe is going to expand forever at an accelerated rate, more than even this whole discussion then, okay? That answers that question. And the other thing also, remember that Mr. Einstein put a constant in his calculations, and then he had to scratch it because of the fact that the universe is expanding. Now it's actually needed. So there is actually, by the way, that constant has to be negative because to prevent the universe from collapsing. So it was acting as an anti-gravity, the cosmological constant that Mr. Einstein put in his equations. So that was acting actually as a negative pressure or an anti-gravity. So now we have a word for this one in here, and it's called actually a dark energy. So there is an energy in here that is actually fueling the expansion more than what it is. So the universe is going to end with this scenario is going to expand forever and ever and ever, all the time cooling down from when it started. And that's basically the end of the universe. Okay. It's interesting. This is one of the biggest topics nowadays in science, trying to understand the origins of the dark energy. By the way, dark energy is just to say that we don't know what it is. It's not related to dark matter, probably. We don't know. Okay. Dark matter is also a mystery. That's another thing also by itself. And the origins of the dark matter is actually around the halo of the galaxies. That's one of the things that started this whole discussion. Actually, Swiggy actually discovered that the fact that the other galaxies far away, they seem to be attracting more than the mass that they have. And now we know also around the halo of the galaxies, stars, as they should be far away from the center of the galaxy, they should be moving less and less fast. Like, for example, the case of Jupiter, which is far away from the sun compared to the Earth, it moves slowly around the Earth compared to the Earth is. The Earth takes 1 year to go once around the Earth, no, around the sun, sorry. And Jupiter takes almost 12 years, and you go around with all of the planets. Mars takes almost 2 years, and Venus takes less because it's closer and so forth. So this is classical mechanics. Mass actually is the one that controls how fast objects move, depending on how far they are. It turns out, for masses that are far away from the, stars that are far away from the center of the galaxy, we expected them to actually slow down too, just like this thing. But we found actually the observations done by Vera Rubin and other scientists is that actually these galaxies are actually not slowing down. So there is also another thing called dark matter, and dark matter, for all we know, is different from dark energy. And the contribution of dark matter to the regular matter to the dark energy is what gives that value of the critical density. Is actually exactly equal to the critical density. So if you add all the matter in the universe, stars, you and I, everything else, and everything, okay? Add all the dark matter in the universe, which is by far more than the regular matter, and add all the energy in the universe, and add all the dark energy, remember the one that is coming from Hubble's constant, and measure, and now divided by the current, basically known the age of the universe and all of that, you will find that the density of the universe is exactly the critical density. But that's a moot point now at this point in terms of how the universe, its fate on how it's going to go. We know it's going to expand forever, even if it doesn't matter what the density is, because at this point there is another force at stake in here that we don't understand that is accelerating this expansion, okay? Okay, this is the whole discussion for this few units. Please go through them, make sure you read them, and if you have any questions, please let me know. Don't forget that we have exams next week. Thank you.